Today's lesson is Keeper 6.4, the fundamental theorem of calculus. All right, so first we're going to look at solving or evaluating definite integrals. And a definite integral is basically an integral that has bounds. So everything that we've done so far was just like the integral of this or the integral of that. It didn't really have bounds. When we actually did bounds, we were using Riemann sums to approximate them, but we don't have to necessarily use a Riemann sum. We could just evaluate it by hand ourselves. So your steps for evaluating your definite integrals: you want to find the antiderivative. So you want to take the integral, and then you want to compute your answer of your top or your b minus the answer of your a or your bottom. So f of b minus f of a. And that answer will give you the area under the curve from a to b. So our first example is to find the area under the graph of y equals x squared plus x over an interval of -1 to 2. And so what I'm going to do to start is I'm just going to integrate it like normal. So I have the integral from -1 to 2, x squared plus x dx. And the integral of x squared is x cubed over 3. And the integral of x is x squared over 2. And I'm evaluating that, so I put such that, or a straight up and down line, such that I'm going from -1 to 2. Notice that I'm always reading from bottom to top when I read that. So from -1 to 2. All right, so what you do when you evaluate it is you're going to take your top number. So I'm taking this 2, and I'm going to plug it in for everywhere I see an x. So I'm left with 2 cubed over 3 plus 2 squared over 2. And then you always subtract the bottom number plugged in. So then I'm going to plug in the -1. I get -1 cubed over 3 plus -1 squared over 2. Now simplifying that, I get 8/3 plus 2 plus 1/3 minus a half. And then adding all that up, I get 9/2. So the integral from -1 to 2 of x squared plus x dx is 9 over 2. All right, so here's like your formal definition of an integral, basically the same thing we just did. If you want to find the integral from a to b, f of x, you're going to take the integral of it, and then you're going to do f of b minus f of a. That is your formal definition. All right, so here's an example. We have the integral from 0 to 3 e to x dx. First thing I'm going to do is I'm going to take that integral. So the integral of e to the x is e to the x, and I'm going to evaluate it from 0 to 3. So again, I plug in the top, and I subtract it from plugging in the bottom. So I get e cubed minus e to the 0, and so simplifying that, I get e cubed minus 1. Again, I do not need a plus c because I actually plugged in values. Next example, we have integral from 1 to e of 1 plus 2x minus 1 over x dx. And we have to assume that x is greater than 0. And we'll talk about why we're making that assumption in a little bit. All right, so again, I'm just going to integrate it straight up. So I get x plus x squared minus ln x from 1 to e. Then I'm going to plug in my top. So I get e plus e squared minus 1. And then I'm going to subtract that from plugging it into the bottom. So I get -1 minus 1 plus 0. All right, now when I simplify that or write that out, I get e plus e squared minus 3. Now the reason why we had to assume that this thing was greater than 0 is because we had the ln x when we took the integral. And remember that x, when you have it in ln, has to be greater than 0. Your ln's can't be negative. So by them telling us that we could assume that it was greater than 0, I didn't have to include the absolute value on the x because I knew it was already positive. All right, next example, we have integral from 2 to 4, 2x cubed minus 3x dx. Integrating it straight up, we get x to the 4th over 2 minus 3/2 x squared. Evaluating that from 2 to the 4. So I'm going to plug in the 4 first to get 4 to the 4th over 2 minus 3/2 4 squared. And then subtract it from the bottom. So minus 2 to the 4th over 2 plus 3/2 times 2 squared. Simplifying that, I get 128 minus 24 minus 8 plus 6, which equals 102. So the area under the curve from 2 to 4 is 102. All right, so what we just did was part 2 of the fundamental theorem of calculus. Part 1 of fundamental theorem of calculus basically puts everything together, and it gives us an understanding of how the derivative and the integral interact with each other. So it's telling us like what happens when I take the derivative of an integral. All right, so this first example, I'm just going to walk you through the steps so we can see kind of what happens. And then once we realize what happens, we'll come up with like a little shortcut. All right, so the first thing I want to know is g of x. So to find g of x, I'm going to integrate the 1 to x t squared dt. So I'm going to integrate that, and I get t cubed over 3 from 1 to x. Now I'm going to plug in my bounds, so I get x cubed over 3 minus 1/3. Now I'm going to take that and I'm take the derivative of it. So I'm taking the derivative of this integral. And so when I take the derivative of this integral, I get x squared plus 0, or just x squared. In other words, if you notice, all I had to really do was take this x and plug it into my function right here, and I get my answer. All right, I didn't really have to do all this work because essentially the derivative of the integral cancels each other out, and I'm just left with the function with my bound in there. All right, so using that same mindset, that same shortcut, I don't have to do a bunch of work. All right, I don't have to take the integral and then take the derivative. All I have to do is take this x and plug it into my function, and I get my answer of 1 over 1 plus x to the 4th. All right, so same thing with this. Again, I don't have to do a bunch of work. All I have to do is plug in my x and plug it into my function for t. Now, the only difference is the x this time is on the bottom. And so since it's on the bottom, remember we do top minus bottom, my equation is going to be negated because it's on the bottom. So instead of just being cosine x squared, it's going to be negative cosine x squared. So again, if it's on the top, you just plug it in straight up. If it's on the bottom, you need to make it negative, make the whole function negative because it's top minus bottom. All right, so next level, we're moving it up a little bit harder. All right, so I'm basically going to show you guys the steps again, and then hopefully once we get the steps, we can figure out a little bit of a shortcut. So the first thing I'm going to do is I'm going to find the integral from 3 to x squared of sine t dt. Now the integral of sine t, we should know at this point, is negative cosine t. And we're evaluating that from 3 to x squared. So when I plug in my top and then subtract it from the bottom, I get negative cosine x squared plus 3. Now, taking the derivative of that, so the derivative of g to x, I'm going to take the derivative of negative cosine x squared, which is sine x squared, and then you remember you have to chain rule it, so I have to take the derivative of x squared, which is 2x. And so I notice that my final answer is 2x sine x squared. Now, thinking about a shortcut for that, you should realize that I still just took this x squared and plugged it in for t. I literally took it and I plugged it into the function. The only difference is because this wasn't just x, I almost have to, if you want to think about it like a chain rule, I have to also take the derivative of this and multiply it by the function. So all I had to do is take the x squared, plug it in, and then take the derivative of x squared, which is 2x. All right, so now doing the next example, I'm not going to do all that work. I'm going to use my shortcut, and I'm going to take this x squared, and I'm going to plug it in right here to my function. So I get sine to the 4th x squared, but remember I have to take the derivative of that x squared as well, so I get 2x. So final answer is 2x sine to the 4th x squared. Now doing that for another problem, I'm going to do it the same exact way. So I'm going to take this square root of x and I'm going to plug it into my function everywhere that I see a s. All right, so I'm going to plug it in for the s squared. This is going to be root x squared, and then over root x squared plus 1. Now again, because it's not just x, I have to take the derivative of that root x. And you guys should know by now that the derivative of root x is 1 over 2 root x. So my final answer is 1 over 2 root x, and then x over x plus 1. Now again, I'm getting x here because root x squared is simply x. All right, so fundamental theorem of calculus part 1 next level. So this is like the top level. If you really understand it, you can really do this. So we're doing the same exact thing, by just plugging in our bounds and taking the derivative of that bound. The difference this time is that I have an x on both my top and my bottom bound. And so I have to use my definite integral formula where I'm taking the top minus the bottom. So again, I'm going to plug in the top bound and also take the derivative of 3x, which is 3. And then I'm going to subtract that from plugging in the bottom and taking the derivative of 2x, which is 2. So I end up with 3x minus 1 over 3x plus 1 minus 2x minus 1 over 2x plus 1. All right. And so again, the 3 in front came from the derivative of the bound on top, and the 2 that came second came from the derivative of the lower bound. All right, so using that same process on this next example, I'm simply going to plug in this x squared and take the derivative of x squared, which is 2x. Then I'm going to plug in this tan x and take the derivative of tan x, which is secant squared x. So when I do that, I'm going to end up with 2x times 1 over root 2 plus x squared squared, which is x to the 4th, minus, so top minus bottom, so minus secant squared, which is the derivative of tan, over 2 plus tan squared x, all under the square root. All right, let me know if you guys have any questions.